We can. I think I should.
हाँ जी, meanwhile so we formally start the session. किसी का कुछ भी सवाल हो, any one of the student have anything doubt, कुछ बताना हो, पूछना हो, this is the time you should, you know, grab the mic and share whatever you wanted to share. Otherwise of course आज है कुछ हम मजेदार गतिविधि हमने आपके साथ प्लान की है. And Ashutosh from our end would share the same. जी, हाँ जी. तो सभी लोग जो है वो हो सके तो कैमरा प्लीज ऑन कर दीजिए. शुरुआत के समय में कर सकते हैं, देन इन द ड्यूरिंग द सेशन इट्स योर चॉइस. बट थोड़ा चेहरे देख लें तो अच्छा लगता है. हाँ जी, सभी जीएनवी स्कूल्स हैं, थोड़ा अपना कैमरा ऑन कर दे हो सके तो. हाँ, जीएनवी बिल्लारी है, दिव्या जैन जी हैं जो जुड़े हुए हैं, जीएनवी सांबा के. हम थोड़ा बच्चे के ना चेहरे देखें तो अच्छा लगता है. I mean, of course, we would be very happy to come and do the workshop at your schools. हम साथ में मिलकर बिल्कुल काम करेंगे. But meanwhile, no, with the help of this online series we are going on, तो यहाँ पे भी थोड़ा अगर आप कैमरा वगैरह ऑन कर दे, so we can see at least at the start of the session we can see some of the face. बहुत बढ़िया, बहुत बढ़िया. ये एम दिव्या है, वो आप थोड़ा बहुत अनम्यूट करके बताएं कि कौन सी स्कूल से जुड़े हुए हैं.
में देख लेना फ्लैप वाला.
फिर विन्ना कोटी शर्मिला जी हैं, आप अगर अपना थोड़ा वीडियो ऑन करके अनम्यूट करके बता पाए फ्रॉम विच स्कूल यू आर ज्वाइनिंग, फ्रॉम वेयर यू आर ज्वाइनिंग. जी यनम जी हैं जीएनवी से, बिल्कुल आप थोड़ा अनम्यूट करके if you can share a little bit about yourself, that would be really great. आज सभा थोड़ी शांत है सोनल, कुछ बाकी लोग किसी और चीजों में एंगेज है. Is it the case?
No, I guess. Anyone, if you want to share any kind of experience, कोई doubt है, कुछ भी है, so this is good time. Otherwise, we'll start the session.
हाँ बिल्कुल. अदरवाइज एटलीस्ट कैमरा ऑन कर सकते हैं शुरुआत में.
हाँ.
फिर सेशन के दौरान आपकी श्रद्धा है. इट्स योर विश, बट शुरुआत में ना सभी लोग थोड़ा कैमरा ऑन कर दीजिए. अच्छा, let me check in security. You should be able to.
Okay, Jay, then let's start the session. I think there's no
So
one is
I
sharing
was just
anything.
wondering, Sonal. So today 47 schools have joined. I mean 47 participants have joined, and of course YouTube में मैं check कर रहा हूँ. YouTube में कुछ 17 to 20 viewers दिखा रहे हैं. So I mean, do they have some other engagement या फिर कुछ any reasons you think that कि आज थोड़े कम लोग जुड़े हैं, कम स्कूल जुड़े हैं? Almost 25% schools have joined.
Yeah, no, there is no such reason. Maybe school में कोई, because today is Thursday also, so
अच्छा
maybe school के बाद, हाँ, we have changed
अच्छा
the date,
अच्छा
so that's why.
अच्छा अच्छा. तो थर्सडे को उनकी स्कूल में और कुछ एक्टिविटीज चलती हैं, ऐसा है? द
हाँ,
रेगुलर
वो अभी
एक्टिविटीज.
स्कूल, हाँ, मे बी इसलिए भी लोग कम ज्वाइन कर रहे हैं. मे बी दे विल ज्वाइन विद टाइम.
अच्छा, बहुत बढ़िया बहुत बढ़िया. ये कबीरधाम वाले स्कूल ने अपना वीडियो ऑन कर दिया है. तो हम चाहेंगे ना थोड़ा सभी स्कूल जो है एटलीस्ट शुरुआत में सभी शिक्षक अपने वीडियोस ऑन कर दे ताकि बच्चों के चेहरे दिखाई दे जाए. हाँ जी, बहुत बढ़िया.
We request everyone to mute themselves. So, welcome everyone. Good afternoon. Welcome teachers and students to the sixth session of Sparkle series. So, I hope you all are enjoying the sessions and you all are learning many new things. So, in the last session, we learned about the computational thinking, जहाँ हम लोगों ने बहुत कुछ सीखा. We learned about the history of computers, how computer helped during the World War II in saving many lives, data encryption, algorithms, and many other things, right? So, in this session, today's session is very important because you are going to learn a very important concept of physics, that is the laws of motion. So, this is a very important chapter of physics, and you will learn about force, torque, acceleration, the historical developments of laws of motion. And we have Ashutosh sir with us, who will be taking the session today. But I hope you all are very excited for today's session, isn't it? Because laws of motion बहुत interesting chapter भी है and बहुत important concept भी है हमारे subject के लिए. So, but before we proceed to the session, we'll show you the web page. We'll take you to the web page. Metri, can you please share the screen? Yes, so we have the Sparkle web. We have this Sparkle web page where we have all the information related to the Sparkle series, and we put the assignment, the attendance, the joining links, the materials required, everything on this web page. So, Metri, can you refresh once? We'll get the assignment link also. Yeah, as you can see, we have uploaded the assignment also, and the joining links are also present on the web page. So, in case if you miss watching the video today and if you want to learn this concept, so you can watch it via YouTube again, right? And now we'll take you to the Hall of Fame. So, yeah. So these are the students with best projects: Alka Kumari from JNV Mohindergarh and Kajal Kashyap from JNV Kabirdham. So last session में you got a code to crack, and these two students have cracked the code. So congratulations, everyone. Congratulations, Alka. Congratulations, Kajal. And then we have the schools with best participation: JNV Solan, JNV Udupi, JNV Nalgonda, and JNV Mohindergarh. So, congratulations, everyone. And as I always say, we want all of your names to be there on this Hall of Fame. So, keep doing the assignments, keep sharing your projects with us, and keep participating, keep learning. So, now we have Ashutosh sir with us. So, Ashutosh, over to you.
Yeah. Thank you, Sonal. I hope I am audible.
Yes, Ashutosh.
Yes. So thank you, Sonal. Thank you, AIF. I welcome all of you. It's great to have all of you back. I took the last session on science of sound, and it was so heartwarming to see that many of you had tried to make those models. And even if you didn't send us the video, I hope you definitely made them on your own and enjoyed making a lot of music as well as a lot of noise on your own. So today's session is on laws of motion. It's a very huge topic, and we are daring to try to shrink it to 1.5 hour session. So let's see how much we can do. But as I said in the last session, probably is your teachers are very competent to teach you many of these concepts and do the numericals, solve those exercises. But our contribution is probably, our humble contribution is to provide you some wonderful activities, some hands-on tangible activities that will make these concepts come alive, that you can see them, visualize them, experience them, hear them, touch them, and in the process gain a very embodied, physical, intuitive sense of these concepts, so that when you do those concepts in your classroom, discuss them with your teachers, they become more alive, more relatable to you. So we'll take up laws of motion today, and let me prepare my slide. So just a brief introduction. Somehow this is inverting. Jay, is this an inverted slide that you're seeing?
No, Anurag. For me, it's absolute. I mean, the proper image.
Okay, great. So this is our beautiful campus beside the river Sabarmati, and we have a small center, small but very lively center for creative learning. And our goal is to bring back the gleam in the eyes of all students, all teachers, and including us adults who work in the lab, and your teachers, hopefully. And this is our small and beautiful lab filled with so many models where we work every day. And this is our auditorium where we have displayed our products. And this is where teachers from across India come and participate in their workshops. We conduct them for 10-12 days. And it's a very beautiful experience for both of us. So you can share your work with us on this email ID. And the homework link is something with my... The homework link is on this. The homework is on this link. So today's session is on laws of motion, and my attempt would be to take you on a journey from Aristotle to Galileo to Isaac Newton. So many times you don't read about Aristotle or Galileo, we just hear about Isaac Newton. But as Newton very famously said that if I have been able to see further, it is only because I have stood on the shoulder of giants. And by which he meant that for thousands of years before him, so many hundreds and thousands of people made small efforts to explore the mysteries of nature, find out those laws, do experimentation, and the knowledge that they discovered and passed on to future generations. That was the knowledge on which Isaac Newton built new knowledge. So if it wasn't for those thousands of years of effort before Newton wouldn't have been able to achieve what he achieved. So that's why he attributed his achievements to the giants who came before him. And two of those giants were Aristotle and Galileo. There were many others, but for our purposes, we'll go on a journey from Aristotle to Galileo to Newton. And what we'll briefly explore are these 4 sections. We'll explore what were the beliefs about nature, what was the knowledge about nature that people had before Galileo, and which we called Aristotelian physics. Basically, Aristotle was a giant who worked on many different subjects, right, from botany, biology to physics, philosophy, logic, and he also worked on astronomy. So he gave a number of laws about how nature works, and the laws of nature or the laws of physics that he gave are vague, are crudely termed as Aristotelian physics. We'll read about the work of, we'll explore, not read, we'll explore in a very hands-on way about the work of Galileo and how it led to the first law of motion. Galileo has a huge number of contributions in other areas, but we'll restrict to mechanics, second law of motion, and third law of motion. So as we begin, this is my first question to you, that in nature, which law starts acting first on a body? कि कोई भी वस्तु नेचर में इधर उधर हिलती है, उस पर फोर्स लगता है, तो सबसे पहले कौन सा लॉ काम करना शुरू करता है? Is it Newton's first law, second law, or does the third law, action reaction, start first and then first law starts acting, or all laws work together, or it depends on the situation? So if any of the JNVs, Sonal or Jay, you could ask them to unmute and answer, it would be great. Make a guess. Which law starts working first on a body? Any JNV would like to?
So it depends on the situation.
Okay. So any law can, so one of the laws can work first. It depends on a situation. Okay. Any other guesses? Can you also think of a situation and tell me which law is acting first in that situation? So like imagine.
First law.
So it is called the first law because it starts acting first?
Yes, sir. Inertia, because of inertia.
Okay. So let me think. So there is an object which is sitting on my table and I try to push it. So will the first law work first or second law or third law? Or depending on the situation, Anju ji said. So can you tell in this situation which law will work first? Can we just one or two more guesses? So it's always good to guess because then you are eager to test whether you are right or wrong. Anyone?
You can unmute and answer, or you can write it in the chat box.
Okay.
Sir, second reaction, second law of motion.
Okay, action reaction you mean? Third law. Usually it's called the third law. Okay. So the right answer is that all laws work together at the same time. So it is quite interesting that we call them the first law, second law, third law. But if you imagine, nature doesn't have a sequence of saying, okay, first law, now start acting. After you finished, now let me apply the second law, then I'll apply the third law. So let's take the situation that an object is on my table. So while it is there on the table, if no net external force is acting on it, let me switch to this. So if the object is on the table and if no external force is acting on it, it is at rest due to inertia, which we call the first law of motion. But isn't the second law applicable right now? So if we say force equals to mass time acceleration, or that the acceleration is force divided by mass, if the net force is zero, so the acceleration is zero. That means its velocity is not changing. So right now its velocity with respect to the ground frame is zero. So it remains as it is because of zero acceleration. And what is the action reaction happening? So the object is there, the earth is pulling it downwards and the object is pulling it upwards. At the same time, the object is pushing on the table downwards and the table is pushing on the object upwards. Something happened? Hello. Hello. Jay, am I?
So
We can hear you, Ashutosh.
Yeah, somebody has shared the screen. So I'll just remove that permission. Okay. Yeah. Continue, Ashutosh.
So actually all of the laws work at the same time. And in fact, it is not only these three laws, all of the laws of physics which are applicable to this situation. So if the object has a particular temperature and if it is more than the surrounding air, it is losing heat. So thermodynamics is also applicable right now. So all of the laws which are acting on it. So if it is a metal box and I put a magnet near it, the magnet is also pulling. But ignoring all these three and limiting to Newton's laws, all of the laws work at the same time. Inertia works at the same time. The force equals to mass time acceleration relation is also working at the same time, and action reaction is also happening at the same time. So it is for our convenience and our classification that we've called them first law, second law, third law. But it's not that that is the way that in which they apply in nature. So I hope that was something interesting for you, and it was interesting for me to imagine, because oftentimes in textbooks also we as adults ask students, okay, in this situation which law is applicable, first law or second law? But if you look at it, even though first law might be more visible in that example, other laws would also be applicable. And now this is my second question to you. So applying a force on a body makes it move. So imagine that we are applying a force which is more than friction. So imagine an object is on a table or floor. Someone has unmuted. Okay. So applying a force makes it move. So the speed of the body increases. And the second point is that if you apply more force in the direction of motion, imagine, then the speed of the body also increases. So then why do we say that the law is force equals to mass time acceleration, or acceleration equals to F by m? Why is it not F equals to mv or v equals to F by m? Why is it F equals to ma? Would anybody like to make a guess? But if I apply force, its speed increases, its velocity increases. More speed, more force I apply, more its speed increases. So then why isn't the law F equals to mv? Why is it F equals to ma? Can anybody guess? Anybody would like to guess?
Sir, if velocity of was always not constant, no?
Sorry?
Sir, it can be because rate of change of velocity is called acceleration.
Okay. But there is a difference between F equals to ma and F equals to mv, right?
Yes, sir.
And there is a reason why it is F equals to ma. But we know that if I apply force, velocity is increasing. So why F is not equals to mv and it is F equals to ma only? So we'll try to answer that as well. So let me take you just a second. So we'll start with Aristotle's physics, and his physics. The first of the postulates can be said that motion continues only as long as force is being applied to the object, and if you remove the force, then the object will also stop. And don't try this with your cats, but I found this nice video of a couple who's playing catch with their cat on a very smooth wooden floor, and you can see that they're applying a force, and after some time the cat is stopping, right? So Aristotle, and this is what we observe in a daily life, that I apply a force. If I stop applying the force, the body stops after some time. So Aristotle said that if the force is being applied, so long as the force is being applied to the object, it will be in motion. If you remove the force, the object will stop. But as you can imagine, there was an obvious problem with this. And you can imagine that there is a archer with a bow and an arrow. After the archer shoots the arrow, somebody's mic is on, there's noise. Yeah. So after the arrow has left the bow, people started asking that if Aristotle's claim is true, then what keeps the object in motion after it has left the thrower's hand? So if I have an arrow, or if I have a ball and I'm throwing it, so Aristotle is saying that as long as I'm applying a force, the object will be in motion. If I stop applying the force, object will come to a rest. But if I throw something, or if I pull the arrow and let it go, so I'm applying the force only as long as the string is in contact with the arrow, or as long as the ball is in my hand. After I release the ball, it is in the air. So now why is it moving? What is making it move forward? That is something that people started asking. And some of the people then tried to come up with this explanation. So what they said, that point one is that the initial force of the bow, of the string of the bow, it transfers power to the air which is surrounding that arrow. And then, as you can see in the top diagram, what they were saying, that firstly the arrow is pushed by the string, and that supplies some power to the air around that arrow. Now as the arrow moves forward, the air in front of the arrow gets displaced and it comes behind the arrow. and then that air pushes the arrow forward. So now that air is in contact with the arrow, so that air is pushing the arrow forward. So as you can see at the bottom, it meant that the air around the arrow is continuously pushing the arrow forward. So do you think this makes sense? That the air around is continuously pushing it. So even though we cannot see air, but air is always in contact. And Aristotle said that force has to be in contact with the body to cause motion. So then people started quite thousands of years. So Aristotle's ideas were prevalent for at least 2000 years. But people started having these doubts over what he was saying is really true or not. So then there was this person called John Philoponus, who lived in about 5th and 6th century AD. And he said that if Aristotle is right, then it would be possible to move an arrow or a rock simply by moving the air behind it. So he's saying that imagine that there is a small rock. So instead of now throwing it with my hand, if air is making it move, then by just putting the rock somewhere and blowing air behind it, it should be able to move. But we know that that doesn't happen, right? So he said that the medium actually resists motion. The air around the arrow is actually slowing the motion. It is not supporting it. And what they said is, it means that power is given to not to the medium, but to the object itself. Basically, they said that when I launch the arrow, the power is transferred to the arrow, not to the air around it. Air is actually trying to stop it. And then this other person, Jean Bourdon, who said in 14th century that this thing that gets transferred to the object, they called it impetus, impetus. And it is that force that gets inside that object. So their belief was that I apply a force to the object, it leaves my hand, that force gets stored in that object, and that makes it move forward, and it dissipates over time, and when that impetus gets dissipated, the object stops. And the greater force I apply, the greater the initial speed of that object, and more is the amount of matter, the greater will be that impetus. And this was kind of the beginning of the concept of momentum, because actually when we say today that this object has momentum, we call it mass into velocity, P equals to mv. So this is what they were also saying, but they believe that momentum is also a kind of force which gets stored inside. So that concept is different from our understanding. Momentum is not a force which is getting stored inside. It's just a quality that we define of the object in motion. Okay. Now, another thing that Aristotle said was the speed of an object denoted by v is proportional to the force F that we apply on it, and inversely proportional to the resistance of the medium in which it is traveling. And the assumption was that the applied force is more than the resistance of the medium. Otherwise, no motion will occur. So I think this is again a very, very intuitive understanding that the more force I apply, the more speed there will be. And you can see that in Aristotle's physics, we have v proportional to F, kind of F equals to mv that we were discussing. And if the surrounding medium is very dense, or if it is applying more resistance, that will decrease the velocity of the object. So v is inversely proportional to r. That's what he said. So now this brings us a question that I have two balls. One is a normal basketball of 500 gram, and the other is a medicine ball of the same dimensions, but it is of 5 kilograms. Now I take them to the same height and I release them. Which of the two balls will hit the ground first? So all of you think I'll ask you the question, and we asked this question in IIT as well. So this is what they said.
Question is, if I drop them from this height, which will hit the ground first? आपको क्या लगता है? भारी वाली.
I think दोनों सेम टाइम में गिरेगी.
भारी वाली जल्दी गिरेगी. भारी वाली. क्या होती है? ये नीचे आपको वैक्यूम में तो दोनों सेम टाइम पे, but otherwise भारी वाली. What about you?
Heavier one.
Heavier one. And what about you? Same.
Okay, so any of the JNVs, what is your guess? Which of the two balls, 5 kilogram will fall first, or 500 gram will fall first? Any student?
So it will fall first, like both will fall together if it is in vacuum.
No. We are not living in vacuum. We are in air. So like.
Then the 5 kg will fall first.
The 5 kg will fall first. Okay. Anyone else? We are not talking about vacuum. We are talking about normal situation. In vacuum, okay. So let's agree that in vacuum they'll fall together. Anyone?
Ashutosh, we have some answers in the chat box also.
Yeah. Can you read them? I'll have to switch my windows.
Yeah, sure. Both will fall. Shreya Dhyani Shed both will fall at same time. Janvi Begal, the ball which have weight 5 kg, and more answers are for 5 kg will fall first.
Okay, great. So you agree with what the IIT audience also said. So let's see if Aristotle can help us. What does Aristotle say? So Aristotle said that V is proportional to F and inversely proportional to R. So V is the speed, F is the force applied on the ball, which is gravity, and R is the resistance of the medium, which is air. So if we say that for 500-gram ball, V1 is the speed and V2 is for 5 kg ball. So gravity pulls the heavier ball more, right? So F1 will be less than F2. And since one ball is 10 times heavier than the other, we can say that F1 ratio F2 is 1 by 10. Now, both are moving in the same medium, right? So resistance of the medium would be same, R1 equals to R2. And so from this top relation, since R1 is R2, we can just arrive at this relation that V1 upon V2 is equal to F1 upon F2. Now let's assume that T is the time taken to travel the given distance. That is after releasing from my hand and until hitting the ground, that is the time T. And if the speed is higher, the time will be less. So V will be inversely dependent on T. V is proportional to 1 by T. So we had this relation V1 by V2 equals to F1 by F2. And we have this relation V1 by V2 equals to T2 by T1. So from these two, we can arrive at this relation that T2 by T1 is equal to F1 by F2. And so T1 equals to 10 times T2. T1 was 500-gram ball. So Aristotle's physics is telling us that the 500-gram ball will take 10 times longer to fall than the 5-kilogram ball. Right? So the heavier ball actually will fall first. So let's see what happens. Right? So both ball fall at the same time. The 5-kilogram ball as well as the 500-gram ball, they both fall at the same time. And it is said that Galileo did this experiment on the Leaning Tower of Pisa. Sorry, not Pizza, Leaning Tower of Pisa. I'm sorry. So, but he actually didn't do the experiment. That's what historians believe. They said he did a thought experiment. He took a heavy ball and a light ball and he dropped them at the same time. And he noticed that both fall together at the same time. So like people had doubts about Aristotle's views before, this was another strong, what should I say, counter argument and counter evidence that Aristotle's physics was probably not working. And another thing that Aristotle deduced, so we'll come back to this thing maybe later, why do they fall at the same time? And I encourage you to do this activity. So the relation of Aristotle, we can extend it that if V is proportional to F by R, and imagine there is vacuum. Vacuum means there is no medium, so the resistance R would become 0. And if R is 0, from this relation you can see that V will become infinite. And if a body has infinite velocity, it will reach any point at any distance apart at an instant. No time will be taken. So he said that instantaneous motion is not possible. So vacuum cannot exist. In nature, vacuum cannot exist. So he was able to take this giant leap of imagination and arrive at this conclusion. Today, we know obviously that vacuum exists. We can create it here on Earth artificially as well as in outer space. Vacuum exists, right? But before we dismiss Aristotle totally as a fool, like there was some truth to what he was saying. So is Aristotle totally wrong? Actually, our daily life experiences, Aristotle derived his understanding and his laws and his conclusions from what he saw around him. And for objects that are moving in air, or if they are moving in water or any oil fluid, it turns out that heavier objects actually move faster than lighter objects if both. So the objects do stop after the force stops acting on it. And these statements are true. And for that, we have to consider these two things. In fact, the first thing only, which is the fluid drag. Drag is basically another word for resistance. So if it is on the ground and I roll it, there is friction acting on it. There's also air resistance. If an airplane is flying, and in fact, even when we drive our vehicles, so for example, we have that accelerator in our motorcycle, and right? So if I increase the accelerator, you must have noticed that after a point of time, even though I keep that accelerator at that higher value, my speed becomes constant. Why? So there is some resistance due to the ground, but there is a large resistance due to the air that is hitting me. So I become at constant speed. So if we consider the fluid drag, then Aristotle's statements do turn out to be true. And that is what he was describing. And with regards to the first point, that heavier object of the same size will fall faster than a lighter object, we have to understand this term called terminal velocity. And your teachers would definitely cover it in class 11th or 12th at some point of time. But in our experiment, we are dropping those two balls from a very less height. If we take two objects at a very large height, we take them very high up, and if we drop them, you will notice that the 5 kg ball actually falls faster than the 500-gram ball. Why? Because it is accelerating due to gravity. Both are accelerating due to gravity, but air resistance is also acting upwards on them. And as their speed increases, the air resistance also increases. And at some point of time, the air resistance will become equal to the weight of gravity. So for the lighter ball, the weight of the force of gravity is less. So a smaller value of air resistance will balance it, and it will achieve its terminal constant velocity at a smaller speed. But for a heavier ball, the force of gravity is larger, so it will take a higher air resistance to balance it, and it will achieve its terminal velocity at a higher value. And so if we take those two balls in a helicopter very far away, they will achieve terminal velocity, and the terminal velocity of the heavier body will be larger than the lighter body. In fact, you must have seen videos of those skydivers falling out from airplane, and then they open their parachute. So they also accelerate, and after a point of time, they reach terminal velocity, constant speed. Their speed doesn't increase because air resistance balances it. So, and this is one paper, very interesting paper I found by Carlo Rovelli, and I would invite students and especially your teachers to read this paper. And in this paper, he discusses that we often discard Aristotle as somebody who gave only wrong things about physics. But based on the discussion that I did briefly with you, his physics makes a lot of sense if we consider all these air drag factors, buoyancy effects, air drag effects. So let's move on. And then came Copernicus, thousands of years, about 1,000 years later, or 1,500 years late after Aristotle. And we know Copernicus for saying that the Earth revolves around the sun. So everybody knows that Copernicus is famous for giving the heliocentric theory, that sun is at the center. It is the Earth and other planets which move around it. But he also said in the same book that Earth rotates on its axis. So we see the stars, moon, sun move across the sky, not because they are moving and we are stationary, but we are moving and the sun is stationary in the sky. Obviously, the moon is moving with us. And the interesting thing is, Aryabhatta, who lived in the 5th and 6th century, about 1,000 years earlier than Copernicus, he also proposed that Earth rotates on its axis about 1,000 years before Copernicus. And these professors at University of St. Andrews have written on their website that people in India who came after Aryabhatta, when they studied Aryabhatta's work and found that he's saying the Earth is rotating, they thought that he's saying such stupid things and he will have a bad name. So let us not make him look like a stupid person. So they removed those commentaries from Aryabhatta's work, thinking that they will save Aryabhatta from stupid errors. So they did not accept Aryabhatta's statement that the Earth rotates on its axis. How can such a massive thing rotate on its axis? But what Copernicus said and what Galileo also later tried to do, there were arguments against what they were saying by the people. So people were saying that how can such a big object move? So imagine there is a big, huge rock. So even to move my table and to move my almirah, I have to apply so much force. And you're saying that this huge earth, this big rock, thousands of kilometers in radius and diameter, how can this move and continue to keep moving? So they did not believe them. And then with regards to the earth rotation, they said that if the earth is rotating, why don't birds flying in the air get left behind? So they're saying that if there is a bird on a tree and you are saying that the earth is moving, right? Now, if the bird starts flying in the air, the earth will move below the a bird, right? So the bird will get left behind. They also said that if I go to the top of a building and I drop a stone from the top of a building, we know that it will fall right at the bottom point, at the foot of the building. So if the earth was moving while the stone was in air, the earth will have moved forward. So the stone should actually fall behind the building rather than at its foot. But that is not what we observe, right? We observe that the stone falls directly below the point that we left it. So why does that happen? So these were their arguments for not believing what Copernicus was proposing. In fact, there is a famous puzzle that used to confuse me as a child, and I'm sure you must have also thought about it. So, is there any JNV from Bhopal or Madhya Pradesh and Kolkata, West Bengal, and Ahmedabad? So, this is the puzzle that I am at Ahmedabad. Okay. Now go into a helicopter. If somebody gives me a helicopter, I go inside. I go into a helicopter, and I take the helicopter and I want to go to Kolkata. From Ahmedabad to Kolkata, I have to go. And instead of taking off and flying in direction of Kolkata, what I do is I take my helicopter straight up. I'll take it about say 1 kilometer up in the sky, and I'll just stand stationary in the air. Now you are saying that the earth is rotating, so what will happen? The earth will rotate below me, and when Kolkata will come, I will just come down. Right? So I take up my helicopter at Ahmedabad. Then it takes about 1 hour for the earth to rotate equal to the longitude or distance between Ahmedabad and Kolkata. So after 1 hour, I will come down and Kolkata will be below me. And if I come down after half an hour, I will land in Bhopal. So is this possible? Can anybody guess? Or why is this not possible if not? Any guesses?
Sir, it is not possible because our helicopter is also rotating along Earth.
Our helicopter is also?
Rotating along Earth.
Okay. But it has left the earth now. So while it was on the earth, so it was sitting on the earth, it was rotating with the earth. Okay. But after going in the air, it is still rotating with the earth. What do you think? Anybody else? One more guess.
So the rotation is very less, like only a little, so we don't notice it.
Okay, so firstly, are you saying that we can travel or we cannot travel? Like
We cannot travel, I believe.
okay. We cannot travel because earth is spinning very slowly.
Yes, sir.
Okay, so assume that I wait for 10 hours. Then I will land in Kolkata.
No.
Okay. So this is something again we should think about. At this point, we'll move on to Galileo. We'll try to come back to this. So Galileo was in like 16th century.
Atmosphere moves with same velocity.
Sorry.
The Earth with atmosphere moves with same velocity.
Okay, okay. And it wouldn't be possible if we were if there was no atmosphere and there was vacuum then? Interesting question. Interesting point. So you're saying that the atmosphere is pushing the helicopter forward. Is that what you're saying?
Yes, sir. I'm from IIT Gandhinagar.
Okay, so you're saying that atmosphere is pushing the helicopter forward. That's why it will also move, it will always remain over Ahmedabad only. Okay.
Yes, sir. Yes, sir.
Okay. Interesting. So we'll come back to this, and these are two very famous books by Galileo. The first one is called Dialogue Concerning Two Chief World Systems, and the other is called Dialogue Concerning Two New Sciences. And here he laid out the new physics that we read today. And to understand the helicopter puzzle, or to understand these questions, that why don't birds get left behind, why does a stone fall at the same place, there is something called frame of reference. So imagine you are sitting in a bus or a train, and you must have, at some point of time, I hope you've thrown a ball up. So if I'm sitting in a moving train or a moving vehicle, if I throw the ball up, does it land behind me, or it comes to my hand again? It comes back to my own hand again, right? So how do we visualize it? We visualize it like this, and this is something I encourage you to do. We have a scooty, maybe you can use a cycle. So let's see what is happening. So he's dropping the ball. He's dropping it vertically. He's not giving it a horizontal speed. Right? You will notice that he will just drop it vertically. He's not throwing it forward horizontally. He's just leaving it. So how is it appearing to us who are standing on the ground? The path is actually like this. We've traced the path. But how is, so this is the path that we are seeing, right? But how is this person who is in the white t-shirt, Pankaj, my colleague, how will he see it? So in the next footage, we'll see how is he seeing. This is what he sees, right? He is seeing the ball going vertically down. And what if he throws the ball vertically up at this point? So he's not throwing it to his left. He's throwing it vertically upwards. But how will the ball travel? So you can see that the ball actually follows this parabolic path. And at every point of time, the ball is vertically above Pankaj. And how will Pankaj see? How will Pankaj see this? Pankaj will see the ball at vertically above him at all points of time. So from the Pankaj frame of reference, the ball is going vertically up, or if he is dropping, the ball is going vertically down. But from the ground observer, the ball is moving forward, which means that even after the ball left his hand, the ball had a forward velocity, which was the same as that of the vehicle. So while he was sitting in the vehicle, the ball was moving forward with him. As he threw the ball upwards, that forward velocity doesn't disappear for the ball. It is still there with the ball. That's why the ball moves forward and it comes back to his hand again. Or the ball moves vertically downwards, but it is moving forward with him. And same thing for the helicopter. So the helicopter is on the earth, it is rotating with the earth. But as soon as it takes off, it still has that forward velocity of the earth. Its velocity doesn't disappear in the forward direction. So as the earth moves forward, the helicopter also moves forward with the earth. And this is what Galileo told people, that you drop something from the top of a building, the stone is also moving forward with the earth, the building is also moving forward with the earth, and the speeds are the same. So from your reference frame, you're seeing the stone fall vertically downwards. But if somebody was in outer space, he would see the stone moving forward. So this was a big insight that Galileo gave, frames of reference, and which helped him put arguments in favor of Copernicus that the earth is actually rotating. And so an interesting challenge and activity for you to do is, so right now what you saw was that if I release the ball, it will move forward, and after hitting the ground it will bounce ahead because it has a forward velocity. So now my challenge to you is this, and you send us a video, make a video that you draw a circle on the ground, and one person can ride a bicycle in that direction, and you can sit on the carrier facing backwards, and you have to drop the ball. So the cycle will be moving, and you have to drop the ball in that circle such that it hits the circle, and after bouncing also it stays inside the circle, it doesn't have to go out. So we tried to do this, and this is what we came up with. So to achieve that, the backward throwing velocity of the ball has to be exactly same as that of your vehicle. So now Pankaj will throw it backwards, and you can see that the ball will fall exactly vertically down. And after falling, it is bouncing on the same place. So if he had released it just like this, the ball would have come forward. So in order for the ball to have zero velocity as it falls, you have to throw it backwards with the same velocity as the vehicle is moving in the other direction. So this is a very nice activity that we did. Maybe it's worth watching again. And this is what you have to repeat. So make a circle on the ground about 1 or 2 feet diameter with a chalk, and try to throw the ball. So you have to throw just when your vehicle is on top of the circle. And you have to adjust your speed, your cycle speed, your throwing speed, so that it lands exactly at the same vertical point. And sometimes these activities look very trivial, but you'll be pleasantly surprised to know that this physics is actually used in how we launch our rockets. So you must be knowing that India's rocket launch center is in Sriharikota, Andhra Pradesh. And if you see in US, I think there is also there's a state called Florida. They have their rocket launch site there. And if you look at the various rocket launch stations across the world, they are mostly near the equator. Why is it that they are near the equator? And the other thing is that rockets are often launched from west to east direction. You don't launch them. So initially we see them going vertically upwards, but as they move up, they start to tilt. So the tilting is towards the east. So that is, they go towards the east. They don't go towards the west. Why is it? It is because of this inertia and this demo that we did. So we know that the earth is rotating. So at different radiuses, the tangential velocity of the earth is different. And you can see these values. So at the pole, we have not shown the 23-degree inclination of the earth, but at the pole where the axis is passing, the point is at rest, so it will be 0 kilometers per hour. But at the equator, at the maximum distance, the earth is moving at 1650 kilometers per hour. Its tangential velocity is that high. So now on the right, you can see that the rocket is actually launched in this direction. So so this is the view of the earth from North Pole. So basically, if you see this figure on the left, you are seeing from top down, from top of the North Pole. So this is what you are seeing. And the earth is rotating anti-clockwise, and the rocket is being launched in the same direction as that of the earth. Why? Because if you launch it in the same direction, you get this 1600 kilometer per hour speed free. Earth gives you that much speed for free. If you go towards the east, why? Because the earth is moving from west to east. So you are already moving with that speed. So you just move in that direction. So you have that much more speed. If instead you go to the west, it will be like throwing that ball backwards. You are reducing your speed. So this simple physics of Galileo helps us launch rockets into space. Now there are so many things that Galileo did, and I'm taking so much time for this initial understanding. There's second law, third law, but it's so interesting to understand how people discovered and made these logic. There is another famous diagram that you must have heard, that how did Galileo find out that uniform circular motion does not require any force. So for that, I'll like to show you this model that we made. In fact, I'll first show you. So these are models that we have made in our own lab. This is an MDF cut kit, and these are iron rods that we have glued on top of it. So you can see it's like a railway track. So these are smooth rods. We have tried to sand them to make them smooth as well. And we have made these from MDF. And you can see that there is an angle over here. and there is another. So this is a down incline, this is an upward incline, and there are markings over here 1, 2, 3, 4. So this is 6, and the same height is over here also 6. 5, same height 5. 4, 3, 2, 1, 0. And then I have a ball, and I have these iron ball. So what I will do is I will release the ball from 6 number height over here. And this is what Galileo also did. He had a different setup. He used wooden railings, and he would release the ball. He made his ramp very smooth so that friction was as small as possible. And he saw that till what height the ball reaches on the other side. So this is one type of ramp. We made another ramp, and which is this. So you can see that my left side, both are almost similar. So these two are identical. The left side is same. But on the right side, this longer ramp has a lower angle, and the shorter ramp has a higher angle, right? So this 6 number height to the rightmost point. Okay, so this is 6 number height over here. This will be achieved earlier because this has a, let me show it like this. Yeah. So these two angles are same. This is 6 number height over here because this angle is steep, and the same 6 number height is achieved over here at a longer distance. So now he said that if I use this ramp in which this angle is shallow and it goes to a longer distance to achieve the same height, now if I release the ball, till what height it will go? And for that I'll show you a video. So these are the two ramps. So you can see over here that on the first ramp, I released it from 6 height and it reached almost 6. There is some friction, so it doesn't exactly reach there. But for the second ramp, it again reaches near 6. So again, here there is friction, so it doesn't reach exactly 6. But the point is, if you make it very smooth, in both the ramps, the ball reaches the same height, even though in the second ramp, the ball has to travel a longer distance. So I'll play this again. Right? And this is what Galileo said, that in the first ramp, the ball is on the left, and after moving to the other side, it reaches the same height. So I launched it from some height, it reached the same height. Now, if I took another ramp in which the angle is shallow, it has to travel a longer distance to reach the same height. So as you can see in the second ramp, it again reaches the same height, but it has to travel a longer distance, and it actually travels a longer distance. Now he took this leap of imagination that if I continue to make the angle of the second ramp lower and lower, and I make it 0, so that after the first ramp, the other ramp is exactly horizontal. Now what will happen to the ball? So he said that the ball will continue to move indefinitely. It will continue to move. It will not stop at all. That was his leap of imagination. That if I make the angle, if I decrease this angle and make it 0, the ball will start from here and it will continue to move forward because it wants to reach the same height as the starting point, but it cannot reach it because this is horizontal. And so the ball will continue to move even though no force is being applied to it. And this is what we call inertia of motion. And this was his great insight, that an object can move even when no force is acting on it. And by no force, we mean that the net external force is 0 and that motion will be in a straight line. And now we can answer one part of our original question, that why do we not say F equals to mv or v is equal to F by m? Because if in this formula you put F equals to 0, your v is also 0. And basically you are saying that motion is not possible without force. which is not true. And the other thing that you are saying is that force is proportional to velocity, that if a force is constant, then it will produce a constant velocity. But we know that that is not true. So why is it not true? We'll come back to that second point again. But the first point is important, that it is not F equals to mv, because if F is 0, your V also becomes 0. So basically we are saying that to have non-zero velocity, I need a force. But right now we showed, and Galileo also said this, that you don't need a force to have uniform motion if you are in a frictionless world. So that is important, that that's an ideal world which does not exist. And later on, Isaac Newton formalized it into his first law, and it has three parts: that if an object is at rest, it will not move unless you apply an external force. If it is in motion, it will not come to rest unless you apply an external force. And if it is in motion, it will not change its direction unless you apply an external force. So even though it might be traveling with constant speed, and if you want to change its direction, you'll have to apply a force, even though after changing the direction it is traveling at the same speed. So a change in direction is also a change in velocity. That's what you read in your vectors, that vector is speed plus a direction. So even if the magnitude of speed is same but direction changes, to change that direction you need to apply force. And there are some very interesting demos that we can do using this first law of inertia, and I encourage you to try doing these. For example, pulling a tablecloth. So you can place some objects, don't start with glass items, start with plastic, or put some stones. Yeah. So you can pull a cloth very fast and the object will stay where the objects are. If you pull it slowly, the objects will also start to move with the cloth. But to pull the cloth while the objects are in the same place, you have to pull it fast. Right, so this was our tapasda. Don't try it with laptop or expensive things. First, you become expert in pulling things. What you have to do is place the objects at the further end of the table, and you roll up the cloth from below and hold it in your hand. And after standing, you pull the cloth downwards. So you have to practice it a bit, but you'll definitely succeed if you try, and you have to pull it fast. And why inertia is in action? Because when you pull it fast, you're applying a great acceleration to the cloth. You're pulling it, you're increasing its velocity in a very short time. But the mass of the objects on the cloth is more, so they cannot increase their acceleration to, they cannot increase their velocity to the same amount in that small time period. So their velocity doesn't increase that much. So their inertia, due to their inertia, they stay in their place, because they will require a much larger force to move with such a great acceleration as that of the tablecloth. There is another thing that you can try is, you can take a ball, take any small ball, and you tie a strong thread to it. So one person can stand on the other side, and what you have to do is you have to swing that ball. There was one person in Lagan movie, right, who used to shoo away the birds like this. And what you have to do is, while swinging the ball, you have to release it so that it reaches the other person. So now you have to guess when will you release that ball. So I'll show you that video. So if you don't release it at the proper time, it will not reach the person. It will go in some other direction only. So now it reaches that person. So if you release the ball when it is, so if the person is standing in front of you and you release the ball when it is here, it will not go towards that person. Why? Because its velocity is in that direction. It will move that way. So you have to judge when you have to throw that ball. A similar experiment that you can do is, we have this toy called 3-in-1, and Manish sir showed it to you in the first session. I'll not show the sound once, but I'll just show that if you put this thing, I think you can all see it properly. There are these two straws, and if you put it in water and you swing it, water comes out. I don't know how visible this is, but you can see that water is coming out. I'll play a video so that it's more visible. So this is a slow motion video, and you can see that the water is coming out in spirals, very beautiful spirals it is coming out in. Right? So my question to you is, if I see it from above, so I am moving the sprinkler like this, and if I see it from above, what will be the path of each individual drop after it leaves the straw? Will it move in a straight line? Will it move in a circle? Will it move in an ellipse or in a spiral like this? Can anybody guess and tell?
Circular path.
It will move in a circular path, right? So after a drop moves out, it will move in a circular path. So let's see this video. So this is a top view. What I want you to notice is that you can see that collectively the drops make a circular path or like a spiral. But I was asking you the path of each single drop, and that is actually a straight line. Because just now we said that to change direction you need force. After the drop leaves the straw, there is no external force acting on the object. So whichever direction its speed was in, it has to move in that direction. So just notice the circle. The circle is following the path of a single drop. You can see that the circle moves in a straight line. Just notice the path of the circle. Can you see it's a straight line? I'll play it again. The circle is surrounding a drop, a single drop, and you can see that the drop is moving in a straight line. Right? So this simple experiment teaches you about inertia as well. Because so if the drop came out over here, and you can relate it to that ball swinging one also, right? After it leaves your hand, it doesn't curve in the air. It will move in a straight direction. That's what inertia tells you. So do try this this thing and observe for yourself that what is the path of. Nowadays, if your teachers or somebody has a phone which can shoot in slow motion, you can also do all of these things. But sorry, somebody was saying something.
I have to continue.
Yes, please go on. Okay, I'll proceed. So we read about these concepts that yes, first law of inertia of rest, inertia of motion. To change direction you need force, but in these real life examples we are not able to apply those concepts. So as I said in the beginning, that we want you to apply those concepts to real life things, make these concepts come alive for you. So do definitely try these activities. That is the fun. Even if you don't understand the concepts, as I said before, you do these activities for fun, and hopefully in the process your textbook concepts will come alive and make more sense to you. Now this is, and one short experiment again I'll show you before moving on to second law, and let's see how much more we can cover. So like the experiment we did with the two balls, dropping them together, but if you drop a paper and a book, right? I have a paper and I have a book. If I drop them, I know that the book falls very quickly compared to the paper. And why is that? Because of air resistance. So actually what Aristotle was saying, that the heavier object falls fast, is true for many objects that we see around us. But you must have seen videos, and if you haven't seen videos, we all keep saying this, that in vacuum if you drop them together they will fall together. right? There is a very famous video also where they dropped an iron ball with a feather in vacuum in NASA vacuum chamber, and both of them fall exactly at the same time. But you don't need a very expensive vacuum chamber to do it. What you can actually do is take a book and take a paper. So you can make the paper smaller than the book. So the paper should be smaller than the book. And instead of dropping them side by side, you put the paper on top of the book and then drop them. And I'll show you a video what happens. So first, we'll drop them side by side and then we'll drop them together. So side by side is obvious, that book falls much faster. Now if you put the paper on top, something magical happens. We haven't stuck the paper to the book, we have just put it on top, right? And they fall exactly at the same time, as if they were falling in vacuum, right? Isn't that wonderful? That you can do that vacuum experiment even at your home. And why is that happening? Because as the book is falling, a low pressure area builds behind the book, and the paper stays in that low pressure area, very low pressure area. So you can approximate it as a vacuum, but obviously it's not a vacuum. So because of that low pressure area behind, the paper is no longer experiencing air resistance, which it was experiencing when we were throwing it like this. So now, since it is not experiencing air resistance, it falls exactly at the same rate as the book, even though book is so many hundreds of times heavier than the paper, right? So do try this very interesting activity. You can even make smaller paper and put it, so you can take a ball and you can put a small piece of paper over here. No sticking, no tape, no glue, and just drop it, and you'll see that both of them fall together at the same time. Then Newton's second law we all know, and I'll not go into formulating and explaining this, but we know that F equals to ma. We all say you can make a very simple setup to qualitatively show F equals to ma. And what we have is we have these wooden blocks, and I'll go to my overhead for this. So you can see that these are wooden blocks that I have, and we've made the wooden blocks of the same size. Although you don't need, so you need only 2 of the same size. You don't need all 4 of the same size. And we have made them very smooth. And what we have done is we have drilled a hole over here. And then we have drilled another hole over here and put a screw. Same thing we have done with this thing, another. So we have these 2 blocks in which there is one hole over here, one hole over here, and there is a screw. And why this screw? Because we will put the rubber band inside like this, and then we'll insert the screw inside so that the rubber band is stuck. And then you will have 2 blocks like this, which you can pull apart and release them. And what will happen? I'll show it to you in the video. Now, if you pull them and release, they will come together and collide. But where do they collide? At the center. Let me show you that first case. They collide at the center because on pulling the rubber band, so when I pull the rubber band and I release it, the rubber band is pulling both of the blocks with the same force. Now if both blocks are of the same mass and the rubber band is applying equal force on them, they will meet at the center. Why? Because F equals to ma. M is the same for both of them. F is the same for both of them. And why is F same? Because of third law. So see, third law is also applicable at the same time. So rubber band is pulling both of them with the same amount of force. So their acceleration would be same, and they would travel the same distance in the same time. So they will meet at the center. Now what will happen if I attach one more block on one side and on the other side I keep only one block? So basically what I will do is I will keep increasing the number of blocks on one side. So now I have 3 blocks on one side and 1 block on another side. So that is what this video is about. So let's see it from the beginning again. And you'll see that the distance of the location of meeting changes. So this is 1 block. Now I place 2 blocks. So you can see that now the meeting point has shifted towards the other heavier block side. Now 3 blocks. So you can see that now 1 block travels a much longer distance. So this demonstrates Newton's second law, that this side there is more mass, this side there is less mass, but the rubber band is still applying the same force to both of them. So this side, which is heavier, will have lesser acceleration. So this will travel less distance and this will travel more distance. So the meeting point will continue to shift towards the heavier side as I increase the weight. There is another also very interesting and fun demo that you should do, and it requires you to have some eggs and faith in science. Although faith is not a word that is used with science, but what I want you to do is you take an egg and throw it as hard as you can, but it should not break. So what will you do so that it doesn't break? And I'll show it to you. So he threw it very hard, but you can see that the egg is not broken. There is no trick. There is some dent in the egg, but it's not broken. So you should all definitely try this. Throw as many eggs as you can. Try it with a raw egg. We used a boiled egg, but you should also try a raw egg. The egg will not break. So why did that happen? If on the other side, instead of the cloth, there was a wall, or I held something solid, the egg would break, right? So there is no change in the amount of force I applied on the egg while throwing. So I am throwing it as hard as I can in both cases, whether I am hitting it on a wall or whether I am hitting it on a cloth. But why is it not breaking when there is a cloth on the other side? Can anybody answer? Why didn't the egg break? Any JNV would like to answer? It's not that I applied a lesser force, but something happened on the other side. What happened? I hope I'm audible, right? Any JNV? If you're still there, I hope this is not boring. These are great activities for you to try and have fun. Anybody would like to take a guess? Why didn't the egg break?
Ashutosh, Megha has written it loses momentum.
Okay, interesting. So it loses momentum, but it is losing momentum even when I'm hitting it on a wall, right? See what is happening. So imagine that this is the wall and the egg is approaching it. So it has some velocity v. After hitting the wall, it comes to rest. Its speed becomes 0. So its momentum has changed. But that is happening with the cloth as well, right? With the cloth also, it has v velocity. After hitting it, it is coming to rest. So the momentum change is same in both the cases, which we call delta p or impulse. You'll probably read about that word, impulse. So the impulse or the change in momentum is same in both the cases. What is different in both the cases? Can anybody guess what is different in momentum changing from v to 0 when hitting a wall versus hitting a cloth? What is different? Any guesses? Time duration is different. The time duration taken to change that momentum is different. So when it is hitting a wall, it is going from v to 0. That momentum change is happening in less than a second, millisecond probably. But when it is hitting a cloth, the cloth is moving backward, it is deforming. So that change in momentum takes a longer time duration. It is taking a longer time duration to come to rest. and that is why its acceleration is less. The force exerted on the egg by the cloth is much less compared to the wall. And so if the force applied on the egg is less, that's why it doesn't break. And this is the concept that is used when they say that why you should wear a helmet, or if you are jumping, as you land on the ground, why you should bend your knees. Because if you wear a helmet and if you meet an accident and hit something, there will be some cushion inside the helmet, so your head will press against it, your head will press against the helmet, and instead of coming to rest immediately, it will travel some distance. The time duration of impact will increase. Same for jumping and landing on the ground. If you bend your knees, you are taking a longer time to come to rest. So the impact force exerted on your knees will be very less. Your knees will not suffer damage. Now, don't try this at home at all, but never ever jump straight on the ground without bending your knees. Your knees or your ankle or something will get fractured, your bones will break. So much impact is generated. So imagine if I'm 60 kgs or you're 40, 50 kgs, if you're jumping on the ground and not bending your knees, how much impact is being generated? So this simple egg activity, Newton's second law tells you why helmets are needed, why you should bend your knees while jumping. And I'll just add these points about second law, that when in second law we say F equals to ma, the F is the net external force. It has to be an external force which will cause motion in the object, and it has to be a net force. What does net mean? Net means that there are, say, two forces. One is in this direction, one is in another direction. Two people are pushing. So one has to, so if both are pushing with the same amount, they will cancel each other out. Net force will become zero. But if one is pushing more, the another one is pushing less, this will move in this direction. Net force will be in this direction. So net force causes acceleration. And when we talk about acceleration, that acceleration is with reference to the center of mass of the object. Now, we can easily understand these 2 points by this slide. Now, this child is very brave and he's trying to push a truck, but the truck is not moving. But somebody can say that by F equals to ma, I am applying a force on the truck. Why isn't the truck moving then? Is Newton's second law wrong? Can anybody tell me why isn't the truck moving? Have you tried to push a truck or a bus? Can anybody guess why isn't the truck moving by this child? Any guesses? I am pushing a truck. I am trying to push a train. I think I am Superman. I want to push a train, but the train is not moving. And I am saying that Newton's second law says if you apply a force, it will accelerate, but it is not accelerating. Why is it that happening? Any guesses? Call out some JNV or maybe. Jay, can you help me?
They have written.
Yeah, go ahead, Sona.
Yeah, they have written mass of truck is more. GNV Ballari writes due to more mass. Anyone who would like to answer, they can unmute themselves and answer.
Okay, so the mass is more.
We cannot break the inertia of truck. JNV Katni writes.
Okay, but Newton's second law says that you apply F. It doesn't say how much force. If you have applied external force, if we go only by F equals to ma, there should be some acceleration. It might be very small, but there should be some acceleration. No, the truck should move. So basically, that's why I wrote this slide, that what is the net external force? And I wrote it on this slide also. So we are seeing that the child is applying a force on the truck, but there is friction also, right? The truck is at rest. Ground is also pushing. The ground is in contact with the tires. So there is some friction force as well that has to be overcome to start motion. So until you apply sufficient amount of force, which is more than that friction, the body will be at rest. And yes, after you apply a force which is just more than friction, it will start to move. And if it's a very big object, the acceleration will be less. There will be very little, or there will be very little motion. So we have to understand what is the net force on the object. And what about this point, this second point, that the acceleration is that of a center of mass. Now imagine that we are applying two equal forces on an object, and they are exactly equal. So the net force is zero. So that means the center of mass should be zero at rest. But if the forces are not aligned, if they are at different axes, it might cause a rotation. That is what we'll see in this small video. So we have put our friend on a very smooth floor on a mat. So both people are applying equal force. So the center of mass of the person is at the same place, but the body is rotating, even though net force is zero. And this is what we call torque, right? So net force might be zero. That doesn't mean that that all parts of the body will be at rest. The center of mass will be at rest, but other parts can move if the forces are not aligned. So they have to be directly opposite to each other so that the body does not rotate. And this is where we can connect Newton's laws to rotational motion as well. So initially we had asked, why is it not V equals to F by M or F equals to mv? First reason we said was, if F is zero, that would mean V is zero and motion is not possible without force, which is wrong. And second point is that if you're applying say 5 Newton force, that would mean that 5 Newton divided by the mass of the object will give you some constant number equal, and that will be the speed. So F equals to mv will mean that constant force will produce a constant velocity, and that is also wrong. This is the difference between F equals to ma or A equals to F by M, that if you put F equals to 0 over here, that means A is 0. And what does A equals to 0 mean? It means rate of change of velocity or acceleration is 0. It doesn't mean that velocity itself is 0. The rate of change of that velocity would be 0. So if the body is at rest and with 0 velocity, it will still be at 0 velocity. If the body is moving, it will continue to move with that velocity in the same direction if the force is 0. And if the velocity doesn't change, that is 0 acceleration. And this is an important point to understand, that constant force changes the velocity in a constant way. Because here also, if I say apply 5 Newton force, 5 by m will give me some constant value of acceleration. So my acceleration will be constant, but that doesn't mean my velocity is constant. So this is the major difference between F equals to mv and F equals to ma. For F equals to mv, a constant force means a constant velocity. But for F equals to ma, a constant force means a constant acceleration. And a constant acceleration means that the velocity is constantly changing. It might be constantly increasing or constantly decreasing. And there is an activity that you should try. You'll have to make some setup for this. But what you have to do is, we have placed a cart with wheels, and you'll see it in this video. And how can you actually feel second law of motion rather than just reading and solving numericals? So we have a cart, we have attached a rope to it. You can see that one person is sitting on the cart with wheels. A rope is attached and a spring balance is attached to the rope. And the person is holding that spring balance. And your challenge is that you have to pull the cart in such a way that this pointer on the spring balance stays in the same place. Means you have to apply constant force, and you have to adjust your walking speed in such a way that this pointer on the spring balance stays at the same place, constant force. And what you will realize, that if you walk at constant speed, you can't do it. For the pointer to stay at the same place, you have to constantly increase your speed. And then you can give a marker to that person and take readings at 1 second interval by a beep. You can put a beep timer on your cell phone, and you will notice that, so this white t-shirt person has to run at an increasing speed to maintain constant force, which means that constant force means increasing velocity. And if you plot the distances, you will see that the distance traveled in each unit of time is increasing over time. So every second you put a mark on the ground, and after you have finished running, come back and see the distance between those markings. And what you'll observe is that in the first second, if it traveled this much distance, in the second it traveled a longer distance. In the third second, it traveled a even longer distance. So that is what acceleration means. That even if acceleration is constant, your speed changes, your velocity changes continuously. Or if the magnitude of the speed is the same, your direction might change, right? So that's what we saw with the ball example, with the sprinkler example. Then there is a very interesting thing that you should do, and this requires you to have a slow motion video. And you must have seen a slinky, right? There is a spring which is called a slinky. And there is a famous demo that people do where they show that a slinky defies laws of physics. It violates Newton's second law of motion. But does it actually do it? Let's see in this. So what I have and what you have to do is take a slinky and suspend it. And after it comes to rest, just release the top part and observe what happens to the bottommost part of the slinky. Sorry. So focus on what happens to the bottommost point of the slinky. Can you see it is standing still in the air? It is hanging in the air. It is not moving. I'll play the video again. The bottom part of the slinky is defying gravity. Gravity is pulling it down. There is a force on it, but its acceleration is zero. The acceleration of the bottommost part. Can somebody guess what is happening? Is it defying Newton's second law? That bottommost point of the slinky, gravity is pulling it down. I have released it from my hand. There is a net external force on it, but still it is not moving. And you should try this. This is not some video editing fake video. You actually do this experiment and record it in slow motion. And you'll see that the bottom part stays still in the air. Can somebody make a guess, why is it happening? Is it defying Newton's second law? And try to relate it to what we have discussed before just now regarding F net and center of mass acceleration. Are there any comments? Or if you want to speak, please unmute and speak. I'll quickly wrap up in 5 minutes. Any comments?
No, Ashutosh, don't have any comments.
Okay. So what we'll do is we will place a ball alongside the slinky and we'll drop it with the slinky at different positions. So in this video, I will put the ball at the top part of the slinky and drop it along with the slinky. So you can see that the ball gets left behind if I drop it at the top point. Now, if I drop the ball from the bottom part of the slinky, let's see what happens. You can see that this time the ball falls earlier and hits the ground earlier than, so the ball is released at the same time, but it hits the ground earlier than the slinky. Now I have to put the ball at the center of mass of the slinky and then they will both fall together at the same time. And this is what I meant, that even though the bottom part of the slinky is at rest, as soon as I release the slinky, the center of mass starts moving at the same instant. So the ball represents the position of the center of mass of that slinky. And that center of mass starts moving as soon as I release it because gravity is pulling it down. So this is a great visualization of the center of mass of the object and how it moves. So the bottommost coil, So the coil at the bottom is being pulled by gravity and it is supported by the tension of the coils above it. As I release the slinky, the top coils start collapsing, but the bottom coil still is experiencing the upward tension of the coils above it, which have not collapsed. And since initially gravity and that tension was in balance, it was at rest. So even after releasing the top coils, it is at rest. It will start moving only when the tension at the top collapses. And that's why until that point, it remains suspended in the air. So this was a discussion of Newton's first law, second law, Galileo, Aristotle, Newton. Third law is usually quite understood by everybody. I'll quickly take 2 minutes and run through it. And basically, this is an interesting video of Newton's third law in daily life. And this is something you should definitely not do. So I'll run that video again. So this person didn't understand that firstly you shouldn't hit animals, but Newton's third law is always acting. So if you are hitting an animal, the animal will also automatically exert a force on you, right? So you hit an animal, the animal will obviously experience a force, but this equal amount of force you are experiencing. And if you are unstable and your mass is less, the effect on you would be more. So a very interesting demonstration of Newton's third law, it can be done using these straws. So what I have are these two straws. These are two flexible straws with this bendy section. What I have done is I have cut this a bit. I'll show it to you in overhead. I have put a slight cut on one of the straws so that I can slide the other straw inside it like this. And then what I can do is, I'll show it to you like this. So I'll blow out air from it. So what will happen? So this is like an elephant trunk. Why is this happening? The air is blowing out from this way. So after hitting here, it is pushing the straw backwards and moving out. So I am getting this reaction force. Now if I turn this straw in this way, what will happen now if I blow? So now you can see that air is coming out this way and the reaction force is being applied on the straw, and so it is moving downwards. Now what will happen if I turn it like this? So one straw is here, then it goes up and it moves sideways. So let's see what will happen now if I blow. So you get a nice spinner. I can change the direction as well. If I change the direction of the straw, it will start spinning in the opposite direction. Oops. So this is a great toy that you can make. Very simple. It demonstrates Newton's third law in a very interesting way. I'd like to show you a video that we made using balloon and some simple straw. So what you have to do is you have to take a balloon, you blow the balloon and you tie a knot, and then you put a straw on it, you tape a straw on it, and then you take some long thread and you take about 4 or 5 meters of thread and tie one end of the thread on the other side, and one end should be open, and here you put the straw, and then so you don't tie the balloon, just hold it with your hand, and as soon as you release it, the air will come out and you will find that the balloon moves forward like a rocket. So this is what you have to do, and it will be visible in this video. You can do a balloon race with all your classmates to see whose balloon goes the fastest. So now in a brief moment you will see. So we've attached the straw to the balloon with tape, and the thread goes inside the straw. And now if you release it, it will go forward like a rocket. And using the same concept, we made even a bigger version. So this is our CCL cycle, which doesn't have any chain, which doesn't have any pedals. but still we are able to make it move by tying a fire extinguisher to it. So you should definitely try this in supervision of your teachers. And if you open the fire extinguisher, it becomes your cycle rocket. So it's a great activity. Let's see it again. We enjoyed it a lot. So the air extinguisher, the carbon dioxide comes on one side and it propels the cycle forward. And this is how rockets also work, and this is why rockets can work in space in vacuum as well, because they are not pushing the atmosphere outside, they are pushing the fuel gas inside them, and pushing that gas out, the rocket gets thrust in one direction. So this is it from our side with regards to laws of motion. There are many other things that you can try with Newton's third law, second law, first law. Some of the things we tried to show you here. There are many other things. Hopefully, some of your teachers would visit, you yourselves would visit IIT Gandhinagar CCL, and we can do all these activities live as well. So thank you so much for joining this session. I definitely look forward to getting videos from you, trying out all these activities. And do send us your feedback videos, and there'll be a homework link as well. So thank you so much for your time and joining. Over to you, Sonal.
Thank you, Ashutosh. Thank you for the wonderful session. So my concepts of laws of motion got revised. I think all of you have enjoyed this session a lot. And अगर अभी किसी का doubt है, if anyone wants to ask any question, you can ask. Like for 2 to 3 minutes, we can have a doubt session. You can unmute yourself, or you can, you can unmute yourself and you can let us know your doubts if you have any.
Thank you.
Thank you so much. Welcome.
Thank
I hope you are not relieved.
Thank you, sir. Thank you, sir.
Thank you so much. I hope you're happy with the session and not just relieved that the session is over.
Thank you, sir.
Welcome.
Thank you, sir.
I think they're quite happy. We can see the enthusiasm in their voice, no?
Any teachers would like to comment, any student, some words, some feedback, even if you don't have any question.
Yeah, you can give your feedback to anyone.
Thank you, sir.
Thank you, sir, for a good session.
Thank you, sir.
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 Welcome.
Thank you.
Okay,
Thank you, sir.
any doubt?
Thank you, sir.
So even after this session, if you have any doubt, or when you practice these activities, you have any doubt, you can mail us at sparklegnv@gmail.com, and we will get your doubts resolved. And you can attend the assignment and everything from the Sparkle webpage. So thank you everyone. Thank you for joining. We will meet next Thursday now with a new session, and we will learn many new things. So keep practicing and keep learning, and do try these activities at home, and do try doing the assignment also. So do the assignment. The assignment link is present. Also, you can go back to any of the assignment, like किसी भी session का assignment आप कर सकते हैं. We have not logged it. So if you want to go back and attend any other assignment, you can do that too. And for this session, obviously, it is open. So thank you everyone. Thank you for joining. We'll meet on next Thursday now. Thank you. Okay, Ashutosh, we can end the session.
Yeah.
Yeah. Thank you. Jay, we can end the meeting now.